the final exam is, I believe it's right on the syllabus, so whatever's there. 2 hours. It's not quite as long as 2 tests would be. I think it's about 7 pages. Most of the tests have been 4 pages. 4, maybe 5. So hour and a half, people will tend to start turning it in. So you should have a little bit more time than usual. Standard format, nomenclature, multiple choice, short answer, mechanism, spectroscopy. Everything we've covered. If you were prepared for each test, then hopefully just take that and you're prepared for the final exam. The test 3 material should be pretty fresh, hopefully. Test 1 material, I would suspect if you look back at that now, and hopefully you have been, you will find it a little bit easier than you did back in August, September, as we've been working with a lot of that stuff. I would suppose that test 2 is where you need most review, particularly on alkene reactions. I'd recommend that puzzle that I gave you. If you remember that sheet, how was the sodium able to learn all the electrophilic reactions or something like that? I will actually resend that email, a fresh copy of that. I would recommend printing that and using that as a review for some of the alkene reactions. At least a starting point. And then you got stereochemistry there for test 2. We've covered UV vis and are covering radical bromination reactions. Those will also be on the final exam. What else can we discuss? Any questions about the final exam? Yes? You want to have a review session? Anybody else want to have a review session? Not sure of when a room is available. I can check and see. Maybe on this Thursday or Friday. I can check to see when if a room is available, and I can let you know by email. Yeah? There are review questions in the workbook, including answer key. There used to not be an answer key to those problems. There is now. Other questions? How much is the final exam worth in terms of points, percentage? 30? And the test average is
22.
45? Yeah. 30 and 45. Okay. I'd be willing to make the final exam average worth 45 and the test average 30 if you would like. That would give you almost half the points for your final exam. Want to raise the grade? Anybody interested in that?
Can we decide after it's graded?
I could do it this way. If it helps you, I could count it 45%. If it doesn't, I'll count it 30.
Yes.
Yes, please.
Yeah.
Thank you.
That way, if you make 100 on the final exam, it'll count almost half your grade. 35%. I'll give you more of a chance. Make a good grade go further. Okay. So after today, we'll see you on, I'll let you know about a review session, but otherwise we'll see you next Tuesday, is that right? Please check the syllabus for when that is. Sounds like it's at 8 o'clock. Got a syllabus right here. May 8th at 8 o'clock, okay. All right, last questions. Yeah.
You have the last labs graded?
Not sure what you mean by last lab, but I have the one that I should have given you on Friday, but I did not. I'll pass those back real quick. Williamson ether synthesis for the Friday lab. No, I do not have the double E2. If you want to pick up the Friday lab, the Williamson ether, please yell. Luke?
Here.
Antonika? Garrett? Lavinda? Jeffrey? Jojo? Morgan? Abigail? Hunter? Kayla? Ruben? Riley Green? Hiral Patel? Sydney? Raquel? Rahad? Michael Stefan? John Yee? Here. Desiree Green? Haley? Winston? Here. Arnav? Okay, guys, let's continue with radical bromination. This is the E2 front page. E2 handout from a while back, the front page of that. We looked at this E2, or hopefully this is, the example. Iodo compound, DBU is a base. They eliminated put the double bond in, E2. Look at the next reaction though. The next reaction they're reacting, it's a radical bromination. NBS, what's NBS used for?
Source of bromine.
Source of bromine radicals. Catalytic AIBN. That's actually similar to peroxides. It's actually a nitrogen sort of peroxide. It's a radical initiator. Carbon tetrachloride as solvent. Reflux 2 hours, 95% yield of this product. Bromination. Got a little resonance there though. It's pretty similar to where we're going to pick up at on the handout. Same type of reaction mechanism. tertiary radical bromination, benzylic radical bromination. These are good places to make radicals. Yeah? How about down here? This is where we've left off, right? Where's the best place to make radical in this molecule? Because this is the source of bromine radicals, right? Mechanistically, what does the bromine radical do? What did it do above?
Makes BH give one of his electrons to crystal.
This reacted with your substrate to form what? In the first step of the mechanism we did. HBr. So the bromine radical took what from your substrate? Yes, okay, this is the thinking you got to do for any mechanism. What? Right? And when it took a hydrogen, it left behind a single electron. It left behind a radical. So where do you want to make a radical at? Yes. Where would be the most stable?
Secondary carbon.
Here?
No, that one.
Here?
Yes.
No. There?
Yes.
Okay. Same place as carbocation. Where would you rather make a carbocation? There, right? Why? Best carbocation you could make would be right there. Why? Windshield wiper over, stabilized by resonance. What do you call such a cation? That cation is called benzylic. What do you call that cation? Allylic? Yes. We're not making carbocations here, we're making radicals. We're going to make it the same position though. Okay? You got two H's. This comes in and this comes here. The H is like, okay, carbon, I love you, but I'm sorry, we're splitting. I'm going to go team up with the bromine electron. And carbon, you can keep your electron, right? And that leads to one H left, but now there's a radical here, right? And we made HBr. You can show maybe eliminating HBr. Then ultimately, this reacts with, we got NBS here. In our mechanism, this reacted with bromine, and we made carbon-bromine bond, and we formed bromine radical. Ultimately, then we ended up brominating here, and so product we can show here would be, I'm not going to draw the H anymore, just put a bromine there. There's also an H there. And that would be an allylic bromination by a radical mechanism. There's another product we could form here, though. How could we have gotten that product? Can you do resonance of this? Yes, we showed resonance before. This electron move in here, one of these move in here, and make two electron pi bond here. The other electron moves out onto carbon. Pi bond here, the other electron moves out on the carbon. True structure is a blend. You got 3p orbitals overlapping. It's one pi system. right? Boom, boom, boom. Everybody sees pi bond over here, right? One electron makes pi bond, right? You see that in this fake structure? But what about over here? Anytime an electron is next to a p orbital, it's going to want to be in a p orbital. So over here, we also got a p orbital, and that's one electron, because it's a radical. But all three of these are interacting. So you got this one system. And once you have this one system, this is sort of the structure. But then if we try to draw that, it's going to be partial bonds, and it's going to be, okay, you can draw it, all right? We draw these fake structures. But the radicals here, they're not cations or anions. So how can we get that product on the right? Instead of the bromine reacting here, the bromine or something quenching here, it can react here. By the way, a lot of you guys are drawing things. You want to add a bromine to this carbon, and some of you guys are just drawing a bromine here. Well, not right. That's 4 carbons, right? If I just draw a bromine here, well, now that's just 3 carbons, right? We need another bond. Here's your carbon, now bonding to bromine, which is what I drew over there. So resonance could give 2 possible products. Up here, we didn't show other possible products because resonance, if we had, we would have put a bromine here. We would have destroyed the aromaticity, and we're not going to do that as quickly, as easily. Here, though, because up here, this is the best product. You maintain your magical aromatic ring. Down here, though, which is the best product, left or right? One on the right. Why? Alkene, more substituted. So actually the major product here would probably be this one if it's thermodynamically controlled. More substituted alkene. It's a lot like a 1,2 versus 1,4, similar to 1,2, 1,4 additions, right? Okay, so you can do resonance of radicals. And if we look back again at that E2 page, that's what was going on there. Where's the best place to make radical in this starting material, 64? Allylic, right? Next door. Either here or here. So they're probably making it here originally, perhaps because it's less crowded. A lot of times you don't know why there's selectivity. Allylic, then we can do resonance structure, right? Electron here, make pi bond there, leave radical here. And after we leave radical here, it captures the bromine, and there's your product. That's how the pi bond ends up here. Now exactly why that's the outcome, it's not really intuitive here. We'd have to look at it in more detail, maybe some advanced considerations. But something made this to be the major product and pretty high yield. That's a radical bromination, including resonance, which made the position shift and the pi bond shift. Interesting, just a side note, what's the difference between this guy and 65? I mean, iodine's a leaving group, bromine's a leaving group. Ultimately, though, what do they do to this? If bromine's a leaving group, this is a leaving group, what's the difference in the molecules? The double bond, yeah. Ultimately, they did this chemistry to put a double bond here. But the E2 elimination put it here. Then the radical bromination put the double bond here, but it also gave back the leaving group. And then what did they do next? They actually did another elimination. Because this product, they've eliminated the HBr. Well, they did more than that. They opened it up. Yeah, it's a little bit of organic chemistry. It reacted here. This became anion resonance. It kicked off. Okay. Not as straightforward as just, I thought they just eliminated it. A little bit more than that. All right, so there we go, a radical bromination example. Back to the other page. Question below. We just did that NBS reaction with the alkene. Why can't you use Br2 in that example? Why did we use NBS? And actually, you cannot use Br2, elemental bromine. Why not? What would be the problem if you tried to use Br2 in that last reaction? What would be a potential problem? Yes, you got an alkene, and we know alkenes react with bromines very easily, instantaneously, to give an addition reaction. Yeah, it would do that. We didn't want that chemistry. Or if you do not, we wanted, what we did was the radical bromination at the allylic position. That's radical. So instead you want to use NBS, which would only do radical. Where bromine could do both, radical, but it could also add to pi bond, to alkene, like we did many times and like you did in lab. You added out bromine to an alkene. So that's another feature of NBS. It won't do the addition chemistry. You know, the bromonium, backside attack, anti-addition of bromine. NBS won't do that. Now again, with benzene doesn't react with anything in this class. So the benzene ring doesn't react with bromine in the other example. In organic 2, you'll learn how you can make benzene react. It requires just a catalyst and a little bit other considerations. Why is only radical bromination generally successful? We already said that. It's because thermodynamically it's the best. Mother Nature just gave us a good reaction for bromine. Chlorine, it's much more reactive, much more exothermic, and it's going to be less selective. So it'll chlorinate non-discriminately everywhere. Not as bad as fluorine. Fluorine's going to be just, like I said, explosive. It's just bromine just has the right thermodynamics. Why is the ability to put bromine on an alkane so important? Did we make this reaction at the top? This was one of the products at the top? We started with just an alkane. Can't do much chemistry with an alkane other than burn it. That's a radical oxygenation. You can also radically halogenate, which is what we did. Why is it so important to be able to do that? Now what type of chemistry can we do with this?
Leaving group chemistry.
Now we have a leaving group. Now you can do lots of things with it. Putting this bromine on opens up lots of chemistry. Now we can do substitution or elimination. You can also do lots and lots and lots of other things which we have not covered. Like maybe make a Grignard reagent, which you will cover in organic 2 from alkyl halide by reacting it with magnesium. So it opens up so many more options once you get that leaving group on. All right, that's why it's so important. I mean, then you're off to the races. For example, maybe you want to react this with final exam, right? Final exam. Let's react this with sodium hydroxide. Show the product. Somebody got something? Can you name your product? That way you can tell me what it is a little easier than. Final exam. Show the product and name it. Somebody have the name of the product? Nathan?
I just don't want to be wrong. I got 2.
I don't want it. What's that song? I don't want to be right.
I got 2-butene, 2-methylbutene.
2-methyl-2-butene, yes, that's it. 2-methyl-2-butene. Everybody get 2-methyl-2-butene? Right? What type of mechanism were we looking to do in DIC? E2? What type of product did we make? Can you describe it in any way? What? Alkene, but what particular alkene? Is that alkene stereogenic? Alkene's not stereogenic. There's no cis or trans. Right? It's not stereogenic. Anybody, any other terminology for what product we formed? We formed Satesef product, yes. Satesef alkene. Know how to name it? 2-methyl-2-butene. Good, good. Okay. Then what if we react this with BH3, it's called borane, and then come back in with KOH and hydrogen peroxide. What would that give? Anybody got it? Can you name it? Now, we didn't look at how to name alcohols in particular, but you can call the OH group a hydroxy group and just name it as an alkane. Anybody got a name of the alcohol? Alphabetical order, H comes before M. Two hydroxy, three methyl. Butane. Yeah, two hydroxy, three methyl butane. Yeah. Methyl here and OH here. Butane, 1 or 4. Hydroxy comes before M, so I'll make this 1, make this 2, 3, 4. 2 hydroxy, 3 methyl butane. So how would you describe that reaction? What did we do to the starting material? We
Hydration?
was it?
Hydration?
Yeah, ultimately we hydrated it. Because if you look at formula this compared to this formula now has H2O added. Now, did we react this with water? No. So when we say we hydrated it, that's just the overall outcome, right? We actually reacted with borane and then this magic step. We actually hydroborated it, hydroboration, followed by oxidation. But overall, the outcome was a hydration. Now, is there any terminology we could use here to describe the hydration? Antimakarnikov, yes. What if we react this with H2SO4? All right. What would that give? Anybody got it? What would that give?
This is gonna form the same thing.
Do it.
That's gonna form the first one.
Give that. Go back to the alkene. Yeah? What else could it give? Anybody have any other alternative? I think mechanistically. You haven't memorized any product. Mechanistically, what's happening? You protonate the OH. What else could you do? Nothing. Okay, after you protonate it, what's next? It just has to ionize. Make carbocation. Then what? The anion, the conjugate base of sulfuric acid ain't going to do anything. So it's not going to add. But you can beta eliminate and put it in the double bond. That's all you can do. All roads take you back here. Think mechanistically. Right? What if we react this with HBr? Everybody got it yet? alkene, HBr. That's the first reaction we looked at other than acid base. What's it going to give? There? Will the bromine be on that carbon? Where are you going to make cation at? Left or right? Text proton, cation here. Bromine has a cation. Bam. Yeah? What if we react this with first sodium, then come in with benzyl chloride? Make this ether, right? Just made that bond there, right? What does sodium do to this alcohol? I'm hesitant to call it deprotonation. That sounds like acid-base chemistry. It's really a redox reaction, and ultimately it leads to formation of the alkoxide. And then we come in here and bam, kick off the leaving group. Good old substitution reaction. We're into the ether synthesis. Ethers tend to be end products. Lots of chemistry. Often called functional group interconversion. Alkyl bromide converted to an alkene. Alkene converted to an alcohol. Alcohol converted to an ether. So you go to different functional groups by your reactions. Let's look on the next page. Okay, examples. This is the synthesis of an anastrozole. A breast cancer drug. Compound here. Pretty common. I believe my grandmother took this drug at some point. Synthesis of it. They're starting with this. This had to be made. What they're picking up here and what they're showing us, what are they doing here? KCN, cyanide. That's a phase transfer catalyst, solvent. Pretty interesting. They're using a biphasic solvent, water and and then dichloromethane reflux. Cyanide is kicking off both bromine, substitution. Cyanide, good nucleophile, SN2, both sides. Then they're coming back with sodium hydride. I don't know if we use that much. H minus. Often used as a base. Good base. Methyl iodide. You'll see this more in organic too, but here, these hydrogens have some acidity. And hydride can remove one and make anion here. So you can make a carbanion by acid-base reaction. Okay? Electron withdrawing groups, very resonance stabilized. You can draw lots of resonance here. And then once you get this, then the methyl iodide, these electrons attack carbon. I've got this drawn reverse. It's best to draw it like this. Attack carbon and kick off the iodine, we end up with methyl here. And they actually do that 4 times. Twice there and then twice over here. That's how they get the methyls on. But then look what they do. NBS, benzoyl peroxide, radical bromination. And where are they putting bromine in? Well, right here, because that's a great place to form radical, because that would be a benzylic radical. So they're doing a benzylic bromination. Why did they put a bromine on? So they can turn around and take it off. But now they come in with this nucleophile. Okay? These electrons then come in here and kick off the leaving group. Because up here, there's only H's here. And you're not going to come in here and kick off a hydrogen. Hydrogen is not a leaving group. But through doing a substitution, replacing a hydrogen with a leaving group, then we can come in here and then we can make that bond. This is a unique or interesting aromatic, but it's got one nitrogen anion there that can be a nucleophile. DMF is a solvent. So, substitution chemistry there, but also a radical bromination. All right, let's look at this here. A little bit of review here, top. Hydration. Okay, we already saw earlier we can do an anti-Markovnikov hydration, right? pH 3 followed by magic step. We can also do a regular Markovnikov hydration. We can either do it with HVO plus, like you did in lab, or you can do an oxymercuration. Oxymercuration, you would have no rearrangement because it's a mercuronium ion. That's followed by sodium borohydride. Okay, Markovnikov to hydrate. HBr. React that with HBr, we would expect this product with the bromine on this carbon, because that's where we would form carbocation. Right? Markovnikov hydrobromination. How would you do an anti-Markovnikov hydrobromination? Because we actually never did that. Although some of you recognize that it was on that puzzle. How would you do this? You do use HBr, but what else do you include? Everybody remember it from that puzzle? Include peroxides. If you include peroxides, you will get anti-Markovnikov outcome on that reaction. Okay? And with the peroxides, this is a radical reaction, not an ionic reaction. Somebody have that puzzle? I don't have a copy of it. Anybody have the puzzle? Okay, let's look at this mechanism.
Dr. Stevens, I got the puzzle.
It's number 17. Right here, HBr peroxides. Whenever you see peroxides with HBr, that's anti-Mrkavnikov addition of HBr. Now here, this forms Br radicals again. All right? But here, the radical reacts with the pi bond. And it's very similar. If it's just HBr, this reacts with the H plus and makes cation, and you make cation here. Well, instead of reacting with H plus, we're reacting with Br radical. And it's very similar. When I say, where do you want to make cation, left or right, you would say left. Okay? Well, where do you want to make radical at here, left or right? Same place, left. So this comes here and reacts with that, but the other electron comes here, and you end up with bromine here and radical here. Same place you would want cation. The difference is here it reacts with bromine first, bromine radical. Now we react with another HBr. But we react in a way to form another bromine radical. So this electron comes here, one of these comes here. Here, the H says, well, okay, bromine, I like you, but I'm going to go pair up with the carbon. And this electron goes here, and what does this give? Well, that gives your product. There's now an H there, right? And we reform Br radical, and so now we can go back and we can react again. Propagation. You can look at this in your textbook. Okay? It was on that puzzle. In the end, if you include peroxide with the HBr, it makes it go anti-Mrkavnikov. Okay, guys. I'll let you know by email about a review session. Otherwise, next Tuesday at 8. Have a good day, guys.